Hi and welcome everyone. This is my first attempt at trying to live code SuperCollider in a YouTube tutorial setting. I'm going to try and show you an idea of mine where I have one synth dev that is playing an audio sample via Playbuff, feeding into another synth dev that is a resonator, and we're going to have the resonator narrow its bandwidth according to a third oscillator that is a sample and hold function, and narrowing until it's almost a sine ringing oscillation. So first things first, I have two buffers here. One is contains a water recording, and the other one contains a brass recording. So let's quickly give them a listen. So that's the water one. And if we change this, that's the brass recording. So first we're going to set up a synth dev for playback, and I follow Eli Fieldsteel's tutorials here, which I've been following along for the last couple of weeks. So we're going to need a reference to a buff num. We are also going to need the rate at which our buffer is playing. We are going to need a start position, which would default to 0 to the start, and a loop argument along with a done action, which we set to done action 2, an amplitude, the attack, sustain and release, of our envelope that we're going to apply to it. And last but not least, the output bus, which we're going to use to feed the signal into another synth. So we need two variables, one containing the signal that's generated and one for the envelope. The envelope is quite simple one. Again, this is very much copy-pasted from Eli Fieldsteel's tutorial. We create a blank envelope and set the levels and the timing between those levels, and the curve parameters. We just make this a linear envelope. The done action for this is going to be 2. Yep. And for the signal, we take our Playbuff. It's going to be a stereo signal. We hardcode this here. Playing our buffer. For the rate, we use the buff rate scale utility class to get the rate of the buffer compared to our audio hardware's playback rate, playback sample rate, so that this always plays back at the correct speed, and multiplied with rate. So we can pitch it up and down. Start pause is our start pause argument, loop is our loop argument, and done action is our done action argument. We could have actually hard-coded this to 2 here as well, but I just didn't bother changing much of that. So that's the Playbuff, and then we're going to multiply it with the master volume of this synth, if you will, and with the generated envelope. And last but not least, we are outputting this at a specified bus. And to make it work, we need to add this to a server. Now let's see if it's accepted. Yeah, of course, I forgot a comma here. So now we have a working synth there. So let's just give that a try. Let's say we just play this. With some arguments. So let's try and just play this with our water buffer. And we have specified a default argument for the output bus, so this should actually just work. Yeah, short, but you can hear it. So next, what I want to do is actually make a routine for that. And this routine will loop synth. Should have copied that. I need to write it out again. And we can also start randomizing a bit here, make it a little bit more interesting. Start pause of some position in the water sample. Somewhere between 20 and 80%. We can also randomize the attack of the envelope a bit, and the sustain time we give an exponent between 0 and 3, meaning it will lean towards 0 a bit more. Of course, this is seconds. And let's also already give this a randomly chosen transposition ratio between -12 and 12 semitones, and convert this to a ratio here. And because we're in loop, we need to wait, of course, and we wait for, again, a random amount of time between 150 and 300 milliseconds. So we looped, we created a routine. So this appears to be correct. Let's just play this. And stop it again. Now, actually, I want to make this a little bit more interesting spatially. So, last but not least, we're going to have a certain amount of routines, actually, that's going to mix in the stereo field. We initialize this with a count argument. Let's say I want 10 of those routines to exist at each time. And of course, we need to we need to set up a routine argument, routine variable to hold all of these routines. And to set those up, we're just going to say we collect over the count, which gives us the index. We're going to need this later. And inside of that, we're just adding a routine to this array of routines. And if we want to play them, we need to again iterate over the routines array and say, please play all of those routines. So now we have a couple of 10 different sequences playing. And of course, to stop them, we need to do the corresponding stop iteration here. Okay, this sounds like a huge chaotic mashup because everything is just centered in the stereo field and there's not much else happening at the moment, but just check that everything works correctly. That's fine. So next we need two more synth defs. The first is a synth def of the resonator. So in the resonator, we need an input bus. We also need an output bus because this is going to be an effects chain. We need a center frequency, which we initialize with 440. We need a bandwidth ratio, which is more or less the reciprocal of the Q factor of the filter. The filter gain decay, which we set to 1 second here, and a pan, because this module is going to get a pan 2 UGen to split everything up in the stereo field. So again, we need a variable for the signal that we're processing. We need an in UGen because we are getting signal values in our synth here. And this is going to be a 2-channel bus. Next, we're going to modify our signal because we want each of those signals presented by the resonators to be mono, so that we can position it in the stereo field. So we just downmix it. And now comes the actual resonator. I've chosen the Reson Z filter here. Probably there are more sophisticated filters in SuperCollider. Just bear in mind that this is just the 5th week or so of me coding in SuperCollider, so I chose the first that did what I wanted to do. So this Reson Z filter is getting the signal. It's also getting the center frequency, and it will also get a bandwidth ratio. And this bandwidth ratio we're going to feed in via a bus. But just to just for demonstration purposes, let's give this a fixed value and pan our signal in the stereo field. I'm going to apply gain later too, but for now just output this to the specified output bus. Right, so we have 2 synth devs. We need to add this again to the server. Seems to accept it, which is good. And now we need to do some setup for our routing between those UGens to work. So what we're going to need now is an array of audio buses. And to make this array of audio buses we say iterate over count, and just please give us back a audio bus of 2 channels on our server here for each of the routines, for each of the paths. So we have an array of audio buses. So what's going to happen now is, instead of just playing everything back from the synth to the audio playback of your sound card, we're going to say we send this to an audio bus, namely the audio bus at index n, since we are in the loop over our routines. And audio buses, and right after the routines start to play, we're going to create 1 resonator for each sub channel. So, and this resonator is going to have an input bus, an input, and this is again allocated to our audio bus. We just sent the signal to. We're going to give it the frequency. Not yet, we're going to do this later. And assign it a random pan. And this is going to be somewhere between left and right and the stereo field. We did add a default argument to the resonator's output bus, so this should just play back at our sound card's output. So let's check if that works. Yeah, so clearly we're getting a resonating output. So now let's go for some more randomization control here. First of all, we're going to give ourselves one random frequency between MIDI notes 60 and 84. So MIDI 2 cycles per second, and we are going to post this to the post buffer just for the sake of controlling that everything's working as it should. So we can give our resonator this frequency, which is great. So each time we are getting another frequency, which is expected. Great. Just going to clear this up a bit. So I'm going to bring up the note tree here. And also the scope. You can see what's going on those channels, on those buses. So last but not least, I wanted to create another synth def for modulating the filter parameters. So synth def mod, we call this mod, and add it to the server. And in it we have we're going to provide two modulation signals, one for the frequency. I call this SH, because we're going to have a sample hold function here, and an output gain. So these are two buses. So both outputting at control rate, one out gain, and we're just going to have this increase in volume over time a bit. Sorry, decrease. no, increase over 10 seconds, sorry. And for the sample and hold signal, which is going to influence the width, the breadth of our filter, we want this to be latched.qr. We want a sample and hold signal which we're going to define, but it will just be triggered every 5 seconds. Sorry, 5 times a second. And we need to also define what that signal is. And this is going to be increasing, so our filter gets more and more narrow. So it's going to be the bandwidth ratio is going to decrease from 5 to 0.001, also over 10 seconds. Keep in mind that the specification of Reson C mentions bandwidth ratio, which is the reciprocal of the Q factor. So what I'm also doing is I'm adding a little bit of ramp noise here. Yeah, at a very low rate, just so it doesn't sound too statically. So right, so this synth def is also added to our server. And what we now need is 2 more sets of buses. One for the, let's call this SH buses actually, so it's more clear. Again, as much as we have routines running. And gain buses. Also as much as we have routines running. Right, so that seems correct. Now what we need to do is in our resonator, we need to change 2 things, because the bandwidth ratio is actually going to come from a input bus, which is specified by BWR, and the gain is also applied from a bus, which is specified by the input argument gain. So now our synth steps are complete, and we need to do is give our resonator access to those. So the gain argument is the corresponding gain bus. The bandwidth ratio argument is the corresponding SH bus. But now we just also need to instantiate our modulator. So this modulator is going to get out SH, and this out SH channel is our SH bus at the corresponding index, as well as the gain, which is the corresponding gain bus. So now I'm going to try just to show off what this synth modulator does, just to pick it out. and very quickly just assign a single bus here. Sorry, out SH. And out gain. SynthDefMD is of course SynthDefMod. So yeah, you can see already that we have a sample hold thing going on here. It's a bit hard to tell. Let's just maybe focus on the first 4. Of course not, because we have to clear it. Actually have to free it, I think. Alright, so there's that. Yeah. It's narrowing and narrowing and narrowing and narrowing until it's getting very narrow and almost ringing. So that's how our synth, our modulator works. So once this is all set up, you should actually be able to hear this. And we do not. So, beginner's mistake. I forgot to instantiate this with correct rate, which is the control rate. So now everything should be working. Different filter frequencies. So let's give this a quick look at the freak scope as well. Oh, we can also try this with the other. Buffer here. Which is kind of nice because we get these. Which is kind of nice because we get this random transposition thing here. So this was like the combined learnings of 5 or 6 weeks doing SuperCollider. I hope you enjoyed it and can get some things out of my unstructured way of doing this. It's kind of new to me to do live coding in this tutorial context, but I believe it's good if you see how I approach things and how errors occur, and you can go about debug them. So, see you the next time.